Welcome everyone to our webinar Wednesday. Today's topic is going to be a flow simulation topic, and we're going to specifically looking at making a medical device better. So we're going to go through an example design problem with a medical device using SOLIDWORKS Flow Simulation CFD to improve that today. And it is part of the larger portfolio of SOLIDWORKS products. You've got your basic CAD tool, you've got data management, communication tools, then we've got our simulation portfolio. And even that in itself is a whole segment with a number of different products. We've got our SOLIDWORKS Simulation FEA tool, which is probably our most well-known simulation tool, but we do also have a motion simulation tool, a mold flow analysis tool, and a sustainability tool for life cycle analysis. But today we're really just drilling in and focusing specifically on SOLIDWORKS Flow Simulation, which is our CFD tool. Now, what is SOLIDWORKS Flow Simulation? It is a general purpose fluid flow tool. It also does heat transfer simulation integrated with the fluid flow. It is a 3D design simulation tool, although we can use it to do 2D problems as well. But probably the most distinctive feature of SOLIDWORKS Flow Simulation that separates it from any other CFD tool is that it's integrated into SOLIDWORKS and it's easy to use. And we like to say that it's an enabler for concurrent engineering, where we take the traditional paradigm where you've got your mechanical engineer working in the CAD tool, they design a product, and then you've got your CFD specialist sitting in the corner cubicle, you hand him a finished model, give him a problem that you want solved, wait a couple weeks, and he comes back with the result. From there, your design either passes or fails, you make a change, and you got to go back and forth with this specialist. Because flow simulation is integrated into SOLIDWORKS and it's easy to use, you don't have to be a true CFD specialist to get some good results out of the tool. It really helps to break down this barrier where the same person or the same team can be working in the CAD tool and doing CFD, and hopefully doing them at the same time. Now, just to get a sense of who's in the webinar today, who I'm speaking with, and your level of experience, I've got a few questions for you. First off, this is specifically a webinar for medical devices. So how many of you actually design medical devices? Okay, just waiting for the last of those votes to come in. I'll share the results with you guys here. So this is pretty interesting. Most of you do not design medical devices. So that's fine. This is still going to be a useful webinar for you, taking a look at SOLIDWORKS Flow Simulation and the capabilities of the tool. It is a general purpose tool, so it's going to work for medical device design, but it's going to work for everything else as well. So I'll try to keep this somewhat general. Won't get too much into the medical details. I'm not a medical device expert myself, so I wouldn't be able to get too detailed anyways. Second question for you guys. How many of you have used a CFD software before? All right, it's looking pretty evenly split here. Go ahead and share the results with you guys. It's about 50-50. You guys have or have not used CFD software. And so I'm interested to find out, related to that, how many of you have specifically used SOLIDWORKS Flow Simulation before? All right. So I'll share that out with you guys. Again, about 50-50. So the poll size was about the same. I got a question in here. It's about 25 people responding. A bunch of people didn't want to vote, I guess. Based on that, looks like everybody here who has used CFD has used SOLIDWORKS Flow Simulation as their CFD tool. So hopefully we'll see some specific things in here. I will try to keep it somewhat general for those of you that haven't used it as well. We'll start from the basics and we'll work our way up. John, in addition to your poll sample size, I saw your earlier question about mesh size. I probably won't get too much into that today, but towards the end of the presentation, maybe we can dive into that a bit deeper. Okay, I think that's enough polling. Let's get on with this. Let's talk about what we're going to go through today. Today's example is going to be this device here. It's going to be a catheter for applying a dosage, and we're going to have some requirements that we're going to design it for. And so we've got our flow coming in from the tube on the backside. It passes through the device. Mostly it's just a straight shot through. And we're looking to have a flow rate of 5 milliliters per second, but we do have some hard constraints. We're concerned about the exit velocity of this device, and we're concerned about the amount of back pressure that's going to be generated, specifically as it fires through this small nozzle at the front here. And there's going to be a couple of key areas that we're going to want to monitor. The valve position might play a part in the amount of back pressure that's generated, and we're also concerned about what type of flow patterns are developed downstream of the valve and if that's going to interact with the actual nozzle itself. And then the key variable that we're going to be playing around with trying to tweak our design is going to be the nozzle diameter in order to get the proper behavior out of this tool. So I think that's enough PowerPoint as well. Let's jump right into the software here. You can see this is my device, and if I take a look inside with the section view, you can see same as the image that I showed you there. We're going to go through and we're going to set up a flow simulation study from scratch, and then I'm going to take you through some other studies that I've pre-run, sort of take you through the process that I used to tweak those variables, show you some of the different capabilities of flow simulation, a couple settings that are specifically very popular when working with medical devices, and then tackle any other questions that you guys have. So let's start this from scratch. We've got our flow simulation add-in enabled, and we're going to go and start a new project. Now I can do this manually, but there is also a wizard available, and the flow simulation wizard is very useful. In fact, I use it every single time that I start a new project. I know a lot of softwares have wizards that are very hand-holdy and slow. This is not one of them, so I'm going to go ahead and grab that wizard. We'll start a brand new project, and I can give this a name. Maybe we'll call this my test 1. I get to choose which configuration I'm going to use, and I'm actually not going to use the one that I'm currently on. I'm going to use this fully open configuration, which is going to have a 0.5 millimeter diameter on the tip of that nozzle. I get to choose my unit system. I'm going to be using SI here. That's what I'm most comfortable with. But you can definitely go through and tweak your unit system. If you're working with medical devices, it's pretty common to measure pressure in millimeters of mercury instead of meters as length, maybe something smaller like millimeters. You can play around with that as needed. We're going to start with an internal analysis where all of the flow is inside our geometry. But we'll actually take a look at an example on this same device later on where we're running an external analysis. There are some other options which I'm not going to use here, but we can incorporate thermal analysis. We can turn on a time-dependent study, so this is a transient analysis. We can include buoyancy effects, and we can even have rotating regions if we have things like pumps in our model. The next step in the wizard is for us to choose our fluid. And this is going to be delivering a liquid medicine. And so I'm going to be choosing water as my liquid. But if you had a specific liquid that you needed to choose or a specific fluid, you could type in your own custom properties here. At this point, using this water, what I'm really doing is I'm harnessing our engineering database, which is full of lots of predefined fluids, predefined materials, and my water has this data associated with it. So I'm extracting the density of the water, the viscosity of the water, and that's automatically included as soon as I choose that fluid. All right, and so this is probably going to be pretty accurate if I've got some sort of aqueous solution being pushed through this device. But we'll actually come back later and we'll switch this up and see how much the effect of a different fluid is on this particular design. There are some small options down here that I'll just briefly mention. This one here, laminar and turbulent. This is a great example of somewhere in flow simulation where the default option takes care of decisions for you. These settings are places where flow simulation really does separate itself from other CFD tools. A lot of them, those specialist level tools that require you to make decisions like, is this laminar flow or is this turbulent flow? And so you have to predetermine what the Reynolds number is, and you have to know which regime you're in. With this setting, laminar and turbulent, we let the software figure it out for us. It makes sense that the software can calculate Reynolds number and can determine where there's laminar flow and where there's turbulent flow. I don't have to be a specialist to know what the effect is going to be ahead of time. This cavitation option, if I think there's going to be issues with that, I can turn that on. I don't think for a medical device that's something we're going to get into. I'm going to accept my default wall conditions for the roughness. Assume we have nice smooth walls on the interior of our device. We've designed it that way. And I'll take my regular atmospheric pressure and temperature as my default conditions. And so that's it. We've stepped through the wizard and we've determined all of the initial conditions that we need other than our boundary conditions. So it's going through right now, it's figuring out my geometry, it's recognizing the fluid volume that's contained within the geometry since I toggled this as an internal analysis. And that's another great thing. I don't have to tell it where the fluid is. Simply by looking at the model, flow simulation is able to understand where there's fluid, where there's solid, and what I'm going to be analyzing. And so once it's done this process, we'll go through, we'll insert our boundary conditions, we'll run our analysis, and we'll start taking a look at some results. So here's my new project that we just created, test 1. I'm going to insert a couple of boundary conditions. My first one is going to be that first requirement. I wanted 5 milliliters per second of flow coming through this device. And so I'm going to apply that at the entrance to the tube. You'll notice that there is a little disc here that I've created. This is something that you need to do when you're running an internal analysis. We call it a lid. Fortunately, there's an automatic lid creation tool in Flow Simulation, so you can simply select the face and it drops that circle in there for you. Of course, even if it wasn't a nice shape like that, I'm sure you guys can model a disc like that, no problem. We've got an inlet volume flow here, and I'm simply going to type in that I want 5 milliliters per second. And I left my units on meters cubed, so I'm just going to type that in as 0.000005 meters cubed per second, and that'll be my 5 milliliters per second. My other boundary condition is going to be on the other end of the device, on the exit. And here I'm not going to be specifying a particular flow rate, I'm just going to be setting the pressure. We'll assume that this thing is injecting into static atmospheric pressure. Maybe if you're injecting this into intramuscular, you'd want to set a different value here. I'm going to click OK for that, and that'll be our assumption for this analysis. Got a question in here. It doesn't matter what side of the lid I click the boundary condition on, and that's a great question. It absolutely does. I want to click on the inside of the lid. That's the side that's adjacent to the fluid. So we're ready to run here. I can go ahead and run this analysis, and I'll be ready to get some results. However, there is an optional step, and I highly recommend using this optional step, and that is inserting goals. What goals are is you're telling the software what values are important to you. If you run the analysis without goals, SOLIDWORKS Flow Simulation has internal convergence criteria, and it can make sure that you reach those convergence criteria before spitting out an answer. However, by explicitly telling SOLIDWORKS which values are important to you, we can make sure that those are the values that converge, as opposed to what Flow Simulation decides should converge. So I'm going to go ahead and insert a couple of goals here. One of the key things we wanted to measure was the back pressure. And so I'm going to grab both the inlet and the outlet face, and I'm going to monitor the pressure on both of these faces. Create a couple of goals for that. I can actually create an equation goal based off of those that's going to monitor the differential between them. And so I'm creating a third goal here, which is going to be based on those previous goals that I set. I'm going to take the pressure at the inlet, and I'm going to use that to subtract the pressure at the outlet, which should be atmospheric based on my boundary condition. And by applying that, I now have a new equation goal. And we'll just rename that quickly and call that back pressure. We were also concerned about the exit velocity, so I'm going to add one more goal. I'm going to grab that exit face, and I'm going to monitor the velocity of the fluid at that face. So that's really it. We're really ready to run the analysis now. We've got our fluid recognized, we've got our boundary conditions applied, we've got all of our wizard steps run through. I'm going to take that study, I'm going to hit run. We can see that the solver is going to mesh and solve the analysis. We can choose where we want to solve this, how many cores of our CPU we want to use. I've got a quad core multi-threaded, so it shows up as 8. If I'm planning to go ahead and run something else and want to keep working on something, I might want to turn this down, but since I want this to go as fast as possible right now, I'm going to leave this on all 8 cores. I've got a question come in here, whether I'm monitoring average velocity or max. Great question. I'm monitoring average velocity, but you could definitely set it to monitor the maximum across that face as well. I'm going to hit run, and this is going to open up a new solve window for us. And this particular analysis is going to run pretty fast, but I'm going to stop it along the process because I want to show you guys some of the things that you can do while it's solving. Now it's just re-recognizing my fluid volume here based on the boundary conditions that I applied. I told it to exclude the internal regions that did not have a boundary condition. You can see in my model there's some of these extra cavities inside the device. We don't want any fluid running through there, just inside the tube. So it's recognizing that for me. Here's my additional solve window that's appeared. And you can see at the bottom there's a status bar. It's currently capturing the mesh. It's saving the mesh, and it's going to start running through iterations of the analysis. Now I mentioned this runs pretty fast, so I'm just going to quickly hit pause on this analysis so I can talk about the two main things that you'll want to do while an analysis is running. The first is insert a preview plot, and a preview plot is a great way to understand what's happening. You can take a look at the results before the solver is even finished. So I'm going to slice along the right plane of this model, and I'm going to monitor, let's say, the pressure. I'll click OK, and I get a preview plot of the pressure at this particular iteration. And then as I continue to run the analysis, you can see that this plot is going to update in real time. If I pause this again, go back, and let's take a look at this plot, but let's switch it to take a look at something like the velocity this time. All right, and so I can see these values as well. On this particular model, you know, the area of interest is pretty small, so might want to go ahead and crank up the size, and we can see that updating. And this is great because if you see something that you're not expecting, you know right away. You don't have to wait for the entire solution. You know, this is a pretty simple analysis at this point, but as it grows in complexity, it takes longer and longer to solve a problem. And you definitely don't want to wait half an hour to find out that maybe you switched around your boundary conditions, applied them to the wrong faces. So it's great to get this feedback right away. If it's wrong, you can stop the analysis and go and fix that before waiting that half an hour. Just going to pause this one more time. The other thing we can do in addition to our preview plot is we can take a look at a goals plot. So not only are those goals great for telling the software the values that are important to you, they're also great because you can take a look at these values while it's solving. And you can see that the exit velocity, that's already been achieved as far as convergence. It's a constant based on my flow rate. And that makes sense, right? It's really just a geometry problem at this point. But my back pressure, that still hasn't converged. It's still fluctuating. So we'll let this keep solving, and we'll see that back pressure approach a particular value. And we can see how that's done over the iterations of this solution. And so once that levels out, software is going to say, all right, we're done. We're happy with that value. The solver is finished. I can close this window, and we'll come back to the SOLIDWORKS interface to post-process our results and understand the effects of the simulation. There are many different ways that you can post-process the results. The first thing that I usually like to do is to take a cut plot, which is basically the exact same as the preview plot that we were looking at. You can track different values just like the preview plot: pressure, velocity, temperature, if you're doing a thermal analysis. And you can also overlay things like streamlines to get an understanding of where the flow direction is. And I'm just going to grab this on the right plane of the model and take a quick look. And as expected, the flow is, very smooth and laminar throughout the entire straight tube. There's a little bit of a twist that needs to happen as it fits through the constriction of the valve. And we were concerned about areas that are traveling faster than 20 meters per second, so I'll type that in as the top, and we can see that this entire nozzle region is moving too fast. Maybe my solution, whatever's being suspended, isn't going to hold together well at that speed, or maybe it's just going to exit too fast. It's going to cause a problem for whatever's out here that we're applying the medicine to. And we can see that that's really just because our constriction is too narrow. So maybe we need to open up that a little bit, or maybe we need to push a slower flow rate. Okay, so a cut plot is a great way to get some understanding of what's happening through your model. The other thing that I like to do right away is I like to take a look at my goals. I told the software those are the important values. Well, let's find out what those values actually are. I'm going to take a look at my back pressure. I'm going to take a look at my exit velocity. And I can see that, yep, it's exiting too quickly. That's over 20 meters per second, the average value across that exit port. And my back pressure, it's 673,000 pascals or 670 kilopascals. We set a maximum of 100, so that's clearly too high as well. I'm not going to have the power needed to drive the flow rate that I'm looking for. So right away we can see that, this design doesn't meet our requirements. So the next thing that we do is we go and improve our design to meet the requirements. That seems like the natural progression. Again, just want to reference the traditional approach. A lot of people are using simulation, or they view simulation as a way to check their designs and verify them once they've completed the design. At SOLIDWORKS, we like to instead think of simulation as a way to help design. So, maybe I haven't finished the design yet. I'm still trying to figure out what the diameter should be. That's the best stage to be using simulation, when we can still go and change this. We haven't built a prototype yet. We haven't locked into that diameter. We can use this as information to help us do the design. It's going to be less costly. And the great thing about this is, because I've built it into my CAD tool, I don't have to go make a change to the model, export that and import that and go through this whole simulation process again. All I have to do is go back to the SOLIDWORKS tab, find the feature that I want to change. Maybe it's this 0.5. Take that dimension. Maybe let's try 0.6 millimeters. When I do that, it's going to update the geometry. Flow Simulation recognizes that it has been updated, so I can update my project, flip back to the Flow Simulation tab, and then simply hit run again. And then I'll have new answers. Now, I've got another question come in here, again asking about mesh size. Does it need to be smaller than the nozzle diameter? Absolutely. You're going to want to have several mesh elements across the diameter of the nozzle in order to accurately capture the behavior through that nozzle. Luckily, right now, I'm using the default settings for my mesh, which is going to be intelligent. It's going to automatically increase or decrease the size of the mesh based on the geometry. We don't have to have a constant mesh size, and in fact you wouldn't want to have a constant mesh size, and the software is taking care of that for me right now. That's all the detail I'll get into for the moment, but we can definitely come back and talk about meshing in more detail later on. So where was I? Right, I just updated the geometry and I'm back in my Flow Simulation tool. All I need to do is hit run, and it's going to solve a new solution based on the new geometry. Notice that I didn't have to run through the wizard again. I didn't have to apply a new inlet boundary condition, a new outlet. I don't have to redefine my goals. They're all exactly the same. All I have to do is click that button, maybe walk away for 10 minutes, grab a coffee, come back, and I'll have new results, and I'll find out whether 0.6 millimeters is large enough. Now, I've actually already gone and done this, and I've taken it a step further, so I'm just going to kill this in the process right here. And we'll go through and talk about something called a parametric study, which is basically this process of going back to SOLIDWORKS, changing the geometry, and then running a new analysis, but automated. So I ran a study, I've called it water, had the same setup as test one, same inlet volume, static pressure, and goals. But I've added to that a parametric study where I've supplied a dimension. I double-clicked on the 0.5 millimeter dimension inside my nozzle, and I specified a range from 5 millimeters to, or 0.5 millimeters to 1 millimeter. The units for this here are meters, so it's a factor of 1,000. And then I gave it a criteria. We know that our back pressure was way too high. It's near 700,000 pascals, and we want it to be less than 100,000. So I set this as my parameter, and I gave it a target value just under 100,000, 95,000 pascals, and I told it to tweak that diameter until it reached that. And then I hit run, and I did this last night before I went home, because it goes through and it runs the study multiple times. So it tries out 1 millimeter, half a millimeter, and then it starts nailing in on values in between. And when I get to the end, I can see that it found I could get close to that 95,000. I gave it a tolerance of 5,000 pascals, so got within that at 91,000 with a diameter of 7.8 millimeters, or sorry, 0.78 millimeters. And so now I know that's going to be the diameter that I want to use if I'm looking for that back pressure. And I can actually take this design point and I create a new configuration and a new project based off of that, and I've got that over here, where I've set this nozzle diameter to 0.78 millimeters. Again, it was the exact same setup, run through my parametric study, run the analysis, and now if I go and take a look at my goal plot, track those two values, my exit velocity and my back pressure, I can see the exit velocity is below 20 meters per second. That's great. And my back pressure, it's down below 100,000, which is perfect. It was a little bit lower, you probably saw, than the 91,000 that we got out of the parametric study. And that's because I rounded. The parametric study had 0.78 and some other decimals after that. I figured manufacturing to closer than just 2 decimal places on the millimeter might be a little bit unrealistic, so I rounded that off. And we can see that even minute changes in the diameter are going to have pretty good effects on that back pressure. So we might need to be cautious as to how we monitor that for manufacturing. Maybe I want to increase that even a little bit more, up to 0.8 or something like that. If I take a look at a cut plot for this one here, we can see that again. Of course, we've got our fastest fluid flow at the nozzle tip, but much less than 20 meters per second. If I go and crank that maximum up, we can see we're not even halfway along the scale. We're looking great. Now, that was my first area of concern. My other area of concern was the valve position, and up till now we've just left it fully open. And what I'm concerned about is, this is a user-operated device. They crank the handle, that opens the valve, or they can set it to close. What if they don't manage to open all the way, or they only have it halfway and the fluid starts flowing out? Is that going to have a bad effect on the exit characteristics of the fluid? Are we going to get turbulence? And so I've created another configuration here where the user has taken that handle and twisted it 20 degrees. Of course, this is going to create a constriction that the fluid is going to have to flow through. It's going to have to bend around it. Luckily, I don't have to set up my analysis again. I just copy that over and I rerun the study. Wait about 2 minutes, and then we get the results that I have here, and we can take a look again at a cut plot or the goal plot and see what that looks like. Right in the cut plot here, we can see that, yes, it does have to move through that constriction. From the colors, we can see that it's not greatly increasing the velocity, although it is picking up some speed as it does have to fit through that narrow area. And it is creating some swirling as well. But